Now let's cover some very basic statistics. This might be a review for some of you, but these concepts represent the building blocks of time series analysis using the statistical approach. In this lesson, we will differentiate between descriptive and inferential statistics. Let's cover descriptive statistics first. Descriptive statistics are a set of values and coefficients that summarize a data set. It provides us with information about tendency and variability. For example, the mean, the median, standard deviation, minimum and maximum values are all part of descriptive statistics. Visualizations are another important aspect of descriptive statistics. They allow us to quickly gain insights and steer the analysis in the right direction. Usually, histograms and scatterplots are often used in time series analysis, and you will see how important they are once we start modeling. Here is an example of a histogram that we will generate in Python in the next lesson. This is especially useful to evaluate the distribution of a variable. In this example, it is clear that the distribution is not normal or Gaussian. Here is an example of a scatterplot that we will also generate in the next lesson. This gives us a good overview of the time series and gives us a hint about trend and seasonality. In this case, we could say that the trend is positive as sales of shampoo seem to increase over time. Now let's cover what inferential statistics are. As the name suggests, they are used to infer properties from a dataset. These properties will help us to forecast the future. Also, this is the time where we test different hypotheses. Now, hypothesis testing is a major component of inferential statistics. It allows us to determine if the trend we observe is due to randomness or if there is a real statistical significance. To do so, we must define a hypothesis and a null hypothesis. The hypothesis is the trend we are trying to extract from the data, while the null hypothesis is its exact opposite. For example, consider the historical global CO2 concentration in the atmosphere. Now suppose that we fit a straight line. Note that we will work this example in Python in the next lesson. Then our hypothesis is that there is a linear correlation between time and CO2 concentration. Therefore, the null hypothesis is that there is no linear correlation between time and CO2 concentration. Then we can run some tests to see if there is statistical significance or not. In this case, the F statistic is large and the p-value for our parameters are less than 0.05. Therefore, we can assume that there is statistical significance and reject the null hypothesis. Another way of evaluating our models will be to study the residuals and analyze the QQ plot. QQ plot stands for quantile-quantile plot. It is a scatterplot of two sets of quantiles. One is a theoretical set, which comes from a normal distribution, and the other set is from the residuals of the model. The QQ plot is useful because if both sets come from the same distribution, or at least a similar one, then we get a straight line. Here is an example of a QQ plot for some model. As you can see, the red straight line is the perfect theoretical scenario. However, we see that the blue line, which represents the quantile from the residuals distribution, is not a straight line. Therefore, the residuals are not normally distributed, and we would say that the model is not good. Before moving on, let's touch on the subject of residuals. The residual is simply the difference between the predicted value from our model and the actual value in the data. Now, we want the residuals to be normally distributed. Why? Because that would mean that the errors between predicted and actual are due to randomness. Therefore, it's a way for us to validate that our model is indeed explaining the variability in the data. Now that we have covered some theory, let's apply what we learned in Python. Alright, welcome to our first coding exercise. Before you begin, make sure that you downloaded the necessary datasets for this lesson. So, of course, this will be about descriptive and inferential statistics, and we will start off by importing all the required libraries for this lesson. So we will import pandas as PD. We will import matplotlib.pyplot as PLT. Let's import seaborn as SNS. From sklearn.linear model, we will import linear regression. And finally, we'll import the stats models.api as SM. And let's put the Jupyter Magic Matplotlib inline. Perfect. Once this is important, I will specify the size for our plots so that everything is nice and big for you guys so you can see, and all the plots will have the same size in the notebook. So plt.rcparams, and then we type figure.figsize, and I will set this equal to 10 by 7.5. Awesome. So once this is done, let's start off with the subject of inferential statistics. And we will start this part of the lesson by importing a dataset. So specifically, we will use here the dataset for shampoo, so the shampoo.csv. So to read the dataset, fairly simple. Data will be equal to pd.read_csv, and we pass in the path to the dataset. In my case, I have it in the same directory, so shampoo.csv. Press enter and the data is now available. So one way to look at the entire data frame is simply to type in data, shift enter, and as you can see, we output the entire data frame in our Jupyter notebook. So as you can see, we have 36 entries, so we get the month and we get the volume of sales for shampoo during that month. This may be useful to display the entire data frame if it is small, but in many cases, the data frame that we will work with will be fairly large. So we can decide to only display the first 5 rows of the dataset, and we do that by typing in data.head. Now, as you can see, we can only see the first 5 rows of the dataset. Alternatively, you can also pass in a certain number of rows that you would like to check. So data.head, and you can pass in 10. And now, as you can see, we get the first 10 rows of the dataset. Then we can also get a summary of the data. So let's write here summary. So the way that you can get a summary of the dataset is simply by using the describe method. So data.describe, and you get the following. So as you can see, you have the count, so the number of instances in your dataset, so 36. You get the mean, standard deviation, minimum, maximum value, and these quantiles right here. Alternatively, you could get the mean and standard deviation with their own methods. So you could do data.mean, and that will give you the mean of the sales. So as you can see, 312.6, and it's the same that you see right here, 312.6. And of course, you can do the same as well for the standard deviation. So data.std, and you get the same standard deviation that you had in the summary. Now let's see how we can generate some useful visualizations in Python. So first, let's go with visualizations, and we will take a look at histograms. So to plot a histogram is actually fairly straightforward. Simply type in data, and then you have a method .hist, and this will plot for you a histogram. So as you can see, fairly basic histogram. So we have the sales, and then on the x-axis will be the volume of sales, and then you have the density right here. So the count, actually. Now this plot is useful, but I would argue that it's fairly ugly. So let's make it a little bit nicer by giving it labels to the axes and cleaning it up a little bit. So we can do, we'll actually use Matplotlib here. So we'll do plt.hist, and then we pass in what we want to plot, which is the sales column. Then let's give it a title. So plt.title will be histogram of shampoo sales. And then we'll give it a label to the x-axis. So plt.x label will be shampoo sales, for example, in $1 million. And we'll give it a label on the y-axis. So plt.y label will be the frequency. Shift enter and you would get the following. So now it's a much nicer plot, more professional. We get the title of the plot, we have labels on the axes, etc. Now, of course, you can customize this plot even more. So for example, you can change the color if you want, or you can also change the number of bins. So let's do that now. So again, we'll use Matplotlib, so plt.hist, and we want data sales. And now we'll also pass in the number of bins. So in this case, I want it to place the data in 20 bins, and we'll give it a nice yellow color. So hashtag FCB-A03. Now, of course, feel free to put whatever color you would like. And again, we'll give it a title. So plt.title is going to be histogram of shampoo sales. And let's give it some labels. So plt.xlabel, again, shampoo sales in $1 million, and give it a Y label. So frequency. Showing the plot now. So as you can see, now we have the data in more bins and we get this yellowish color. Now another modification that you could do to the histogram is combine it with a density plot, for example. And for that, we will use the other plotting library that we imported, which is Seaborn, that we imported as SNS. So let's see how we can do that now. So we will say that SNS.distPlot, so a distribution plot. We pass in the sales column that we want to plot. And again, I will specify that bins is equal to 20. I will say that hist will be equal to true. KDE will be equal to true. And again, I will give it my yellow color, FCBA03. Then we give it a title again, so histogram of shampoo sales, and we give labels to the x-axis first, so shampoo sales, like so. And on the Y label this time, we will give it label of density. Now, as you can see, we get a slightly different plot. So now on the Y axis, we get density. And we also have this distribution plot that we see here. So it allows us to quickly take a look at the distribution of the data, see if it is normal or not. And as you can see here, this is not approaching a normal distribution. Now, another type of plots that we will be using a lot are scatter plots. So let's take a look at how we can make some scatter plots in Python. Again, fairly straightforward. We can use Seaborn again, so SNS.scatterplot. We pass in X, so this will be the month column. This is going to be on the x-axis, and y-axis will be the data for sales, so data sales. Then we give it a title again, so plt.title will be the historical sales of shampoo. On the Y label, we will say sales of shampoo in $1 million. And on the x-axis, we will say it is the month. We can display now the plot, and as you can see, we get a scatter plot of our data. So with descriptive statistics covered, let's move on now to inferential statistics. And for that part, we will read a new dataset containing data on CO2 concentration. So a new section in the notebook, which is Inferential Statistics. And we will import the new dataset. And this time, like I said, this is the CO2 dataset. So CO2 data will be equal to pd.read CSV, and then the path to the CO2 dataset dot CSV. And let's display the head of this data frame right away. So as you can see, this is the data that we get. So we have the year, the mean, global CO2 concentration, and so on. So now let's only focus on the data from 1950 to the end of the data frame, which I believe is in 2016. So we'll only consider the data from 1950 to 2016. So I will say that my independent variable x is CO2 data year dot values, and then we only take from 1950 to the end. And my dependent variable, so the observed data, will be CO2 data, and we want the data mean global. We want its values, and again, only from 1950 and onwards. And now we can make a scatter plot of the data to see how it looks like. So SNS.Scatterplot, and we say that x is capital X and y is equal to y. Awesome. Of course, we'll give it a title. So this is the historical global CO2 concentration in the atmosphere. And then we give it a y label, which is CO2 concentration in parts per million. And of course an x label, which is just going to be year. Now plotting this, you should get the following plot. So you see we get our title and we have our data points increasing over time. Now let's try to fit a straight line to the data. A linear model might not be the best choice here because as you can see we have this little curve going on right here, but let's consider this as a baseline for now. So let's get our data ready to be modeled. So x, I will simply reshape it, -1, 1, and I will do the same with y. So reshape -1, 1. Now the data is ready to be modeled. I will initialize the linear regression object. So linear regression, which is what we imported from the sklearn library. And then we can fit the model. So reg.fit, and we'll fit on x and y. Then we can print out what is the slope and intercept for our linear regression. So we can say the slope is, and I'm using an f string is, so the slope is stored in reg.coef underscore first element, and the slope is, and this is reg.intercept underscore first element. And as you can see, you get the following. So the slope is 1.36. Oh, sorry, I wrote slope again, and I meant intercept. Sorry about that. So the slope is 1.36, and we get an intercept of negative 2,348. So now, what would that mean? Does it mean that at year 0, the concentration of CO2 is negative? Of course, no, that's not what it means. But this is, for now, a baseline model that can approximate the concentration of CO2 between 1950 and 2016. So now we can also plot our straight line with the data to see visually how well it fits the data. So our independent variable x is CO2 data year dot values from 1950 and onwards. Y is CO2 data data mean global dot values from 1950 and onwards as well. Now our predictions coming from the linear regression model that we did earlier are going to be reg.predict, and we predict on the reshaped x, so -1, 1. And now we get our predictions now that are stored in this variable. And now we can plot the straight line and the original data. So I will say that plt.scatter, so I will make a scatter plot of X and Y, and I will specify that our data will be with black dots in this case. And I will also add our straight line. So again, the independent variable is X as well. Y is going to be equal to our predictions. And in this case, it will be a blue line. Let's also give it a line width equal to 2. And now, as always, we give it a title. So plt.title is going to be historical CO2 concentration. plt.ylabel will be the CO2 concentration in ppm. And the X label will be the year. Finally, we can show the plot like so, and you get the following. So as you can see, the straight line is not a perfect fit, and it's actually pretty hard visually to say if it's a good model or not. So one way to check is to print out a summary of the model. So let's take a look at the R-squared, F statistic, and let's see if our coefficients have a p-value that is less than 0.05. So actually, to do that, we will refit a linear model, but using the stats model library this time. So very simple. Well, the way we do it is X is equal to SM, so the stats model library that we imported, dot add constant. We pass in CO2 data year, dot values, sorry, and then 1950 and onwards. And then we say that the model is sm.ols, so ordinary least squares. That will fit a linear line. So CO2 data, pass in data mean global, dot values from 1950 and onwards. And we pass in X, and we can fit right away. Once this is done, we can print a summary for the model. So model.summary. And you should get the following. So as you can see, the R-squared is actually fairly high, 0.97. We also get an F statistic that is very high as well, which is an indicator that, the straight line might be a good fit to the data. And as you can see here, for both our constant and x1, so the intercept here is the constant and x1 is the slope. As you can see, those are the same values that we got from the previous linear regression. Well, the p-value is very small. It's not necessarily 0, but it's way smaller than 0.05, which suggests that the coefficients are relevant, and so that the model is a good fit. But is it really? So let's check that assumption by studying the residuals of the model. And specifically, we will display the QQ plot. So to do that, we can extract our residuals, and this is equal to model.resid. And then we can plot the QQ plot. So QQ plot is equal to sm.QQplot of the residuals. And the line will be equal to Q. And of course, let's show the plot right here. And you should get the following. Now, what do we see? Well, clearly, the line in blue is the one coming from our residuals, so from the fitted residuals, and the red straight line is the one coming from the theoretical normal distribution quantiles. So what do we see? We see that the blue line is not a straight line, and we see a clear departure from normality, since it is not a straight line, right? So therefore, we would say that this model is not a good fit in these situations, because clearly the residuals, so the errors, are not from a normal distribution, so they are not due to chance, to randomness. And we can further prove that by looking at a histogram of our residuals. So we will take a look at their distribution. So fairly easy. Let's plot a histogram of our residuals. So plt.hist of residuals. And quickly you can see that this distribution here is not normal. And so we would conclude in this case that the linear regression is not a good model for predicting CO2 concentration. So thank you very much for taking this free preview with me. As always, there is a link in the description below if you want to take the full course. The link will have a promo code applied to it already, so you can click on the link and you'll get the course with 87% off. And if by any chance you click on the link and the promo code has expired, feel free to send me an email. It will also be in the description, and I will send you a coupon code so that you get the course on sale. So thank you very much, and I'll see you on the next one.